Hi, everyone. So today I have Drew with me, and we're going to go through the basics of AO Core and explain to you, as best we can, all the different things that Hyperbeam, the implementation of it that we've been building, now does in practice. So there's so many different things to cover here that I think we're going to probably start to some extent at the end and show like what we can build up to. And then we'll go back to the beginning and work out or work through together how the system works, why it behaves in the way that it does, and also, perhaps more interestingly, for the non-technical audience, why we're so excited about it. We really think that this is a new infrastructure for a decentralized web, and it now exists in one box and can be done, executed in a trustless manner. It's a huge, huge step forward. Still lots of janky, rough edges to fix up, but it's in a pretty good spot now.
Spoiler alert, it's pretty cool.
Okay, well, we'll find out. All right, so as an example of pretty cool, how about one day you woke up and you were like, what I really need is a oracle of Bitcoin prices created by Coinbase that is trustless. And I want both the USD price and the Euro price.
You'd have to pay a bunch of money for some API, right?
Not just that, but the developers to build it for you.
Yeah.
It would be a huge, huge thing. Well, in AO Core, that can actually be done in one HTTP request. In fact, you can even do it from your URL bar in a browser. So here we've put together this path, and this looks long and very complicated, but we'll explain in this video how it works. And you can see here that we've executed this path on this node, and it's given us back a signed attestation from that node. And that node could be running inside a TEE. We've run it locally so that you can see what's happening. Yes, but you can see that this has resulted in the price of Bitcoin in euros and dollars being submitted to, which is a little bit depressing today, being submitted to...
Ignore that price. Ignore that price.
A new process that we have inside, running inside a Hyperbeam node or running in AO mainnet general. And so if we say inbox here and we look at the second item, we can see that it is a message that has the Euro and USD prices of Bitcoin. And that was done in just one URL.
So in like one line, like if you're a crypto native, you know what an oracle is. But if you're just tuning in, you're not. Like oracles are basically like, here's the regular web, and here are other blockchains, and they need to talk to each other, and they don't. And so the business of doing what Sam just demonstrated, which is getting real-world pricing data from out there, and then integrating it into whatever blockchain project you have, maybe it's a financial swaps or something like that. Those are huge businesses with like massive numbers of employees. I mean, they're some of the most watched projects in the space, and you just did that in that line.
Yeah, in the URL bar. It's like Chainlink as a link, ironically.
Okay, that's
Chainlink as a hyphen.
Pretty mind-blowing.
We think it's very, very, very cool. It turns HTTP into a distributed, verifiable, and trust-minimized compute network, and then turns your URL bar or curl or whatever tools you use for operating with paths, essentially, into... You could think of it kind of as a shell. And so we're going to explain how all of this works in this video. But basically, we've made it so that the URL bar is generally programmable and the results you get from it are provable.
The way I think of it is like you've taken the regular web, and it's almost like it's two-dimensional right now. And you've added this third layer of functionality like that. You've made the web 3D in a way where you've infused new functionality into, but it's still the regular web that we know, and I recognize the URL bar, but now it can do more stuff, a lot of really cool, unprecedented stuff.
Yeah, one of the things it does is that it makes all computable states in every single program, and I really mean every single program, not just programs that are entirely inside the system right now. It gives them a computable address. So you can say, for example, here we have a result. It's got an ID, and we could just take this ID and say, okay, I'd like to extract some part of that. So in this case, the Euro price. And the state, each little bit of state inside every program is addressable and subsequently remixable. So here we had this computation state, like we did that big pipeline of different interactions. And at the end, we got another, essentially a short link, but you could have used the full hash paths to access it, but then you can do whatever you want with that content that you find there.
So there's two things here. And one, before I get into the remixability part, I want to talk about the trustlessness part, where like, I guess someone could have scraped the Coinbase website. But if I wanted verifiability that, the euro price was this price at this time, it's a little bit of like a trust me bro situation.
Right, precisely. Like almost all oracles actually are just a trust me bro, which is, not viable if the whole point of the industry that we're working in is to make things trustless. And basically the way that AO Core works is that everything is a device, like a small piece of functionality, and you can layer those pieces of functionality together such that something, for example, like, we had no intention of using the URL bar as an oracle, particularly for anything other than just like curiosity that it's possible until preparing for this demo. But then we were able to put together the path that reused a bunch of existing functionality in new ways because it is open and composable. And it's not just like one virtual machine like the Ethereum virtual machine or the Solana virtual machine or even WASM. We have support for WebAssembly as a virtual machine inside it, but it's more like a meta virtual machine. It's a way of expressing any type of state transformer and expressing the inputs and outputs such that you end up with this. Yesterday in the video when we were shooting it, I don't know when it came out, I guess you guys have presumably already at least had access to it. We were talking about how it's almost unhelpfully
novel.
I think we're in that zone.
Yeah.
And I actually think that this is a good opportunity to just show people how it works. It's much easier to kind of grok when you see it do stuff than when you hear someone trying to explain it.
The remixability thing to me, for just based on what I've been hearing from you over the past months and years, is like where the unhelpfully novel goes into the bounds of people who you're just not even, it's like we can't even comprehend the end of what it can do. I'm curious though, I want to see if there is another demo that might help us grok that before we jump into it.
Right, yeah, we can maybe start at the beginning. I mean, my sense is very interesting. Building Arweave permanent information storage. It's super simple idea. The implications are not easy to exhaustively enumerate, but you can at least see like what it does from 3 words. AO Core is unfortunately and excitingly in a way very the analogies that we would normally draw upon don't really normally exist. Or sorry.
No, they don't exist. They don't exist because not only are there technological sort of ramifications that are hard, but there's also sort of like the societal economic ramifications too, and combined it's like a real head spinner. I mean, I guess let's
let's just show people.
We're teasing people about the remixability, but while you're pointing it up, one of the most interesting things I had was like what the future looks like for devs in a world where information is infinitely remixable, and what that would do to sort of like the business of software development. But anyways, I'm rambling.
Well, no, I think on that point, like the APIs that developers are used to using today, they're kind of exposing just a tiny fraction of the AO Core version of the same idea. Those APIs are just taking like the finished, polished product and only a small part of it and making it available through some interface. In AO Core, because it's layered in, it's a HTTP computer, if you will, every single subcomponent of every intermediate state is addressable. You can take that and remix it and pull it into your other programs and do whatever you want with it, write scripts on top of it.
The world is your oyster.
The world is your oyster. I was going to say infinitely remixable, but then I was like, is that technically accurate? Or is there like a limp? Probably 2 to the power 256.
Until the heat death of the universe,
Sometime before then. Okay, yeah, so here, this is the most basic thing you can do with a Hyperbeam node. Now, when you see localhost 8734, that means it's talking to, on my machine here, this Hyperbeam instance that's running on my device. you can see here my address and the version and some configuration information. But other than that, it's just a normal Hyperbeam node. We'll be using both this local node and also some remote nodes at different times in this demo, so that we can see what's happening in the backend and also use other types of trusted computation system. So here, though, what we've done is just go and get a single ID from Arweave. Now, I think this is the first place where we might deviate from people's expectations of what AO is. If you're in the Arweave community, I think there's reasonable odds at this point you still think of AO as some kind of smart contracting system. And that is definitely one of the things it can do. But that's like the literal tip of the mountain, where actually all the things underneath it are useful for a ton of other stuff too. But so, okay, we're getting a piece of data from Arweave. In the backend, what has happened here is that Hyperbeam and AO core implementations in general have or will have different, what we call them, stores. They're like sources for IDs. And so here, what will have happened is this ID was not found locally, but it will have gone to an Arweave gateway, in this case, and downloaded that ID. Now, if you didn't want to go to a gateway, you could index Arweave yourself, and there's a device in Hyperbeam that lets you do this. And then you could access that piece of content, and you have no centralized dependencies or even external dependencies. You run that Arweave node next to your Hyperbeam node, and then you have decentralized full access to the network. And so, yeah, we have this result. But if we look at it in the network tab of our browser, which we're also, I'm afraid for the non-tech people, we're going to be using this a lot, because it shows us what's happening in the, you say, like the programmable layer of the system. So one of the things we find here is that not only do we get the result in human viewable form, we also get the tags from that piece of content. So if we were to go to the view block for the same ID, we would find that each of these things that we have here as a header is a tag on the underlying piece of content on Arweave. And so this is a bunch of metadata. And also we find this signature and signature input section. And what these allow us to do is to transfer the fully verifiable Arweave data item to another node. In this case, to a browser, but it doesn't really matter. It could have been to another Hyperbeam node. They treat each other sort of one and the same. And as a consequence of doing this, you can get full data item verifiability just built into the browser. This is something that would be very easy to add to Wander if they wanted to. But say you didn't want to do that. Say you wanted to just access this piece of content. You don't want to modify the browser. You don't want to have a web extension, and you still want to get absolute verifiability of the content that you're seeing. Well, what we could do is go to a TEE protected node. And a TEE protected node, for those not in the loop, is a trusted execution environment. Essentially, this is a piece of hardware where, in the same way that if you're sort of familiar with this concept in crypto of a ledger or some sort of hardware wallet, there's a hardware isolation zone inside the CPU where the data is encrypted, or rather decrypted, for execution just inside the CPU in a very small part, actually, of the die. But when it is written to RAM anywhere outside the CPU, then it is encrypted. And so that means even if you are the owner of this device, if it is correctly configured, you can't see what's going on inside it. It is a black box. And this is what enables us to add a layer of trustlessness, or at least very strong trust minimization to a computation that's occurring inside the system.
And you can't have a remixable open web if that trustlessness or trustworthiness wasn't there, because if you aren't certain that what you're remixing upon is guaranteed by the TEs, then what's the point?
Exactly. Well, what you end up doing is paying for trust. So we've been operating the Arweave.net gateway since the launch of Arweave many years ago. And when we do so, we have to execute that code ourselves, because otherwise, until Hyperbeam, we didn't have a way to trustlessly farm out that computation. But this is one of those things that Hyperbeam gives us. So here, dev-compute-1.forward.computer is a TEE node. We go into this ID, and it will give us back the content, and we can go and it will have the same headers in it that we were looking at before. Okay, but how do we know it's in a TE, right? Like I told you it was, you trusted me.
I trust you, yeah.
But that's not sufficient, right? We want to be able to really prove that this is running in a trustless way. Well, what we can do is we could, on, for example, a local Hyperbeam node, we could ask it to go and get an attestation from the TEE. So this is the SNP device, the Secure Nested Paging. They have a terrible name for this.
I've been calling it the SNP device in my head. Yeah.
Okay, yeah, SNP device, sure. It's going to generate an attestation for us and send it back to our node, which is going to verify it with its SNP device. So our node is going to verify the remote node. And when we do this, after a couple of seconds, we'll find it says true. Okay, that's cool. But this still requires us to run our own node, right? Well, you could actually delegate this to any other node in the system to essentially bootstrap trust. So if there's one node that you trust, you can use that node to bootstrap trust in other nodes. And to do that, all we would do is basically run the same thing, but on, say, we trust devcompute2 for some reason, then we can execute this, and it will give us back true. So we know that all the nodes are agreeing. This is a real connection to a SNP executing machine. And it's not just executing AMD's SEV SNP architecture, which is a real mouthful.
That is a mouthful, yeah.
Yeah. It's executing this particular set of software and hardware. And what's really cool about this is that it's not just like saying, it's an SNP machine. It's got it on the CPU. It's saying, no, the kernel that's being executed has exactly this hash. The init RD, it's part of the sort of bootstrapping of the operating system that's running on top, has exactly this ID. And then the append, that's the full operating system, in this case it's running Hyperbeam OS, must have this hash. And even below that, the firmware of the device, actually the microcode of the CPU, must have exactly this hash. So when we get back that true, it looks kind of casual, but it's really not. Yeah.
It's a powerful truth. Talk to me about the cost of trust and the setup of the internet right now. So we have this trustless web. We were looking at what you're doing. We see the possibilities. I could see someone out there say, okay, so what's the difference though? I could go to AWS and I'm fairly confident that they'll run my compute. What is the advantages of this method?
I mean, there are multiple.
Yeah.
There's sort of quantitative, which I think is probably, if they're in that camp, maybe we start there. The more skeptical. It's very simple. Trust is incredibly expensive. If you go to Amazon, you try and buy storage, it will cost you approximately $23 per terabyte a month. Now, think about it. If you go and buy a hard drive, it costs like a couple of $100. And the hard drive doesn't last if you do the math, you find that is an astronomical price for storage. But people still do it when the most efficient storage market out there is actually decentralized storage market. Is Chia, although unfortunately they just burn the storage. They fill it with random data. But it's from the point of view of the person providing the storage, it's all the same. And they charge in the order of 15 to 20 cents per terabyte month, depending on time and the token price. But this is incredibly cheap. This is like a factor of 100.
As a fraction of AWS.
Yeah, a tiny, tiny, tiny fraction. And so then you got to ask, well, hold on, if storage is available at that price, why is everyone?
Yeah, why?
Yeah. And the answer is pretty simple. It can only be two things. Distribution, right? So AWS benefits from bundling services. Everyone knows of AWS. You're using it for CDN or something.
I see their ads on TV. Yeah.
Exactly. Yeah. Or, and I think this is a huge, huge component, trust. Just think about it. Okay, someone came up to you and they said, look, buddy, I'm a Chia miner, and they're paying me 12 cents per terabyte a month. I'll give you storage at 20 cents per terabyte a month. And the cheapest you can possibly find online is maybe Backblaze B2, I think, is $5 or $6 per terabyte a month. So this is a incredible deal. You're not going to believe them. No. Right. And so the point of trustless networks is to make it so, well, you don't have to believe them. They can prove it to you in a succinct, transmissible proof.
Gotcha. So the cost for storage and for compute, at minimum, just one aspect of the trustless internet plummets.
Yeah, enormously. And that's just storage. But it scales in largely the same way across all types of hardware provision. And one way to think about Hyperbeam, this system that we've been building, is that it is a decentralized physical infrastructure network operating system. It is an OS built directly for the hosting of all these different devices, which are really just ways of marshaling resources. So, for example, here we have this relay device. Well, what that's doing is marshaling the download of the host machine, right? And you can get back this, if we look at the network tab here, and I'm sort of skipping around in the flow here, but no. Once it's spoken to the other node, we can see that it's served us with a signature. And somewhere buried in here, we'll see the hash path. So it said, hey, I executed this computation, and here's a signature from my key, which you can verify through these other mechanisms, whether you trust it or not, that this is the correct output at this position in essentially the global computable state space.
And so I'm buying what you're selling in terms of the trustworthiness, let's say. We keep talking about remixable here. And I'm intrigued. I know we've talked about what that means, but in your own words, a remixable internet, what does that mean to you specifically?
There's sort of two sides. They are, under the hood, kind of the same stem, but they're so different in the way that people would see them that I think that it's worth handling them separately. One is content, right? Remixable content is something we've been talking about with the PermawebOS for a long time. You upload a piece of content, today we're viewing this in a web browser. Didn't need to be in a web browser, right? It could be in, or it could be inside someone else's application. All they would need to do is just get the data.
Yep.
So the content is all remixable. Then there's the systems of computation. And for example, when we saw this, we've lost it now. Yeah, the path earlier when we were looking at the Coinbase Trustless or Trust Minimized Oracle, there's a little component in there where we were running a script. And that script basically was filtering out 500 other currencies they'd given us and just picking 2, euros and dollars. Well, that's remixable compute. You can take any state, because the states all have this sort of universal format. You can take them and you can apply other types of computation that weren't really intended, let's say, for it on top of it. And the closest analogy here, I think, is if you're a developer using something like Bash. Bash is a command line environment, and Unix did this clever thing at the beginning where they said, okay, we're going to make one universal data format. And that data format is a stream of bytes. It's a file. Everything is a file. And by layering on top of that many different, essentially reuses of the same core idea, they had a transmission layer between applications. I think the simplest way to look at this is that just like Unix had this model that everything was a file, everything in AO is a message. And a message is simply a collection of keys and values. Under the hood, it's a little bit more general than that, even, so that you can express things that aren't just a normal sort of message, but are like a tree and more cryptographically efficient and a whole bunch of stuff. But generally, the notion is, or can be imagined to be at least, everything is a message, and the messages can have keys and values inside, and you can do with them what you want. And this is just like how in Unix, they had this notion that everything is a file, and subsequently, all of the different programs can interact with one another using this one unified format and subsequently be composable and remixable. So, for example, we could use the echo program to say hi, Drew. And then we could pipe that into the TR program that will allow us to, in this case, delete the colon from this input string. And so because everything is a file, this program actually says that it's reading, it's called standard input. And that's where we're going to find the standard output that was directed from this echo program. And doing this, you can build up these like enormous pipelines of complex functionality that's created by just remixing simple, small blocks. And then, instead of trying to build a monolithic solution that is everything to everyone, you can instead build these small, what we call devices, that are basically just state transformers of messages. You get a message in and a message out. Actually, two messages in, the sort of base message that you're working on, and then the request. And that can have parameters and things inside it. But then you get, one way or another, a simple single message as the output.
Mm-hmm.
And that can be passed between any type of device. So if we go back to, this one, say, we can see that, okay, what we're doing here is constructing this pipeline. And we can get back to this. This is a more complex one. You can see here that our base message has this device, the relay device, which is taking a request, this second component here, and that request has inside it that the path that we want to go to is this other node that's nested, and it's a little bit confusing, but basically what that's doing is saying execute this request on top of this base, and the base has nothing but summon for me, essentially, the relay device. And then on top of the output of that, call the verify function inside the snip, as you were calling it.
The snip.
The snip device. Exactly. And then that is summoning the right tiny bit of infrastructure for us to execute that single resolution.
So a world where this is widespread would look something like, I'm Drew, I'm making a little fun app. Got this cool little app, but it's not anything that's enormous in size or scope. But then, my friend Jeff is looking at my app and says, I'll be darned if there isn't something in some part of that I could see for my app. And he's able to accurately and trustlessly take that compute and then apply it to his app and build on top of it.
Yeah, take the compute or take the state.
The state.
Yeah, and because literally everything is a message, even this item from Arweave, we can say, authority. So we can say, hey, who are the compute authorities that are able to write to, or you see this rendered in the browser as a image or a short video. But actually under the hood, it's also an AO process. And so you could extract out who's the authority for that process and then go execute on top of that, or perhaps filter by that. So you only find the processes that have that compute authority.
So we just established a world where the compute and storage really cheap because it's trustless. And then we now have a computing and internet world where it is effortless to mix and match without ever having met anyone, different state to design and iterate as we will. So first of all, what you're telling me is that there is going to be an explosion in the future of apps and development in general, right? Because it's now super cheap. It's now effortless to sort of cobble together your own quite compelling app without any sort of team or know-how. What does that world look like to you? I mean, that's a very rich and I would imagine incredibly healthy ecosystem. But I'm curious, this is what we're talking about, where it's so hard to unlock what AO does, because there's a technical aspect. There's also a societal. Yeah.
Yeah, I mean, I think we have some forebearers, you could say, of similar ideas, different environments. But one that sticks out to me is the world of Linux. Where everyone can take code and remix upon it, and each of the programs uses this universal format for things to talk to each other, so they're composable. I mean, obviously, the big difference is that Linux runs on a single person's machine, and everything outside of that they have to go and get and interact with through these it's remote, you could say. AO is different in that there is no remote and local. Actually, each of these paths that we've been looking at, these are addressable addressable states that are shared between all machines to some extent, at least could be recomputed on all machines that can run that device. Something I guess we haven't touched on yet, but it's probably worth saying is that, so this is the, relay device, and that's one of the built-ins to Hyperbeam. But you don't have to have it built in. It's kind of like an app store. You can go, if it can resolve the name relay at 1.0 to a piece of executable code, and the node is configured to execute that code, it would just go get it on demand and run it for you. There's some stuff we want to do there, and I think we should probably say everyone in general, this is such a huge project. Progress has been great, and we're in a pretty solid spot, I think. But there's still a ton to do. Like making it so that you can load native compiled code is not something that it does yet, but you can load Erlang code that it might compile to as like an intermediate language. But this is a technical minutia. But the idea basically is that you can load devices from Arweave itself and then recompute stuff. And so it's a new type of computer, I think is the only way to say it. And there really isn't anything that's quite like it. The web is like a distributed knowledge graph. This is like a distributed compute state graph. And it's radically, radically different.
Yes, that is very clear.
Yeah. Okay, cool. So now we have that established. Right, we had our image here. But what if we wanted to get it from a TEE? So we've gone and proved that we can verify that remote node is running inside a trusted execution environment. We will get back signatures. So once we verify the SNP device, we can also look at the attestation that it made to the key that lives inside it. And then when we get a result, we can go look in the headers here and see who signed the result. And so we can check that they're the person we expected them to be. We have an open PR for, we haven't yet merged. Okay, this is localhost, so it's not secure. But if you're on a trusted connection, you can look at the certificate and basically make it so that the certificate or the SSL connection terminates inside the TEE. And subsequently, the certificate can be for the same address in AO. So your like browser has a provable connection that you can see with your eye, and you look at this certificate is valid. The public key in the certificate here, you can see this number and you can check it against what you would expect for talking to that particular TEE. It's like trustlessness right to the edge of the box without any special software, using just the normal infrastructure of the web. You could then prove that you're speaking to the right node.
It's like web in 3D. It's pretty incredible.
I don't know what 3D means here, but I guess if that's your way of seeing it, sure. It's a different type of web, but that's for certain. Okay, so yeah, we can also access full applications. So here's StarGrid.
StarGrid, shout out.
Exactly. Which we're accessing again from a TEE node. So if for some reason,
StarGrid battle tactics.
thank you. You can see here that something cool about this is we have support for manifests. If you're an Arweave developer, you know that it's not just like one TXID. You normally upload a whole bunch of data at once and then allow your or in your application then sort of pass between different parts of it as if it's like an immutable file system. And yeah, that's just another device in Hyperbeam because why not? And it wouldn't even need to be a device. You could do this with one of the existing virtual machines. Say meta virtual machine after all. So now we have established that yes, you can get decentralized and trustless access to content on the Perm web, which has been
a long time coming.
A long time coming. Yeah, nearly 8 years building Arweave now, and finally you can do it. It's pretty cool. Why don't we look more at the sort of the fundamental primitives of what AO Core is offering? And I think the way to do this is look at one use case. So say you wanted to have a decentralized version of a particular compute service that AWS offers. Mm-hmm. It's called Lambda. Basically, the idea of Lambda is that you have functions as a service.
Okay.
And instead of booting up virtual machines, large virtual machines at least, to run your code and have it be sort of, you like ship this big container thing and it runs for a long period of time and is sort of stateful, we could say. You can just spin up these micro machines that are running just one function, and you can do it very quickly, and you can do it in a massively parallel way. It's a logical service for Amazon to offer, but right now there's really no decentralized. Well, there was no decentralized alternative. So let's see how we would do that with Hyperbeam and AO Core. So first thing that we want to do is we want to just upload a function. Now here we're going to be using the Lua device, but we don't need to. We could use the WASM device, as we saw in the initial demo, that was marshalling a Genesis WASM. We call it virtual machine, but running WASM code in the backend. And here we're just running Lua, but it really could be anything because it's a meta virtual machine rather than a virtual machine. It allows you to basically cryptographically link the inputs and outputs of other state transformers. And another word for a state transformer is arguably a virtual machine.
I hear universal translator. Is that about right?
Universal transformer.
Transformer. There you go.
Yeah. That's for sure. And the magic comes from the cryptographic linking of the inputs and outputs of the transformer. Again, no good words for it, but over time we'll make them. All right, so we send this. Okay, cool. So now we have an ID that's been returned. And the reason it was returned was because we called the stroke ID, or just the ID key on top of the message that we sent with this post request to our node. And it says, okay, I'll run ID on it. And it's a message at 1.0, or rather, sorry, actually in this case, it's a Lua, a 5.3a device message. And when I run ID, long story short, just gives me back this hash here. Okay, so then I could go to this hash and I could say, cool, in the browser, for example, let's say a device should return to us. The device of this is piece of code. Great. Okay, but what if I now want to use this as a function so we can recall it? But why don't we instead try to execute the piece of code? And what it does, we can read here, it's just a one-line function. It takes the base and it looks for a value called total inside it. And it basically adds the request value x to the total if it already exists, or set the total to 0 and then add the request. Then it returns a new state. And so we can take this and we can say, okay, and x equals 2 means, so every state transformation has that base and the request, and we're taking x from the request. And so here, by adding ampersand x equals 2 in this particular part of the path, we're basically programming AO to go and add this 2 into that particular part of a pipeline. And then once it's executed that, it's going to be building up that hash path and the attestable sort of blockchain structure, if you will. It's certainly cryptographically linked structure. Again, there's no great word for this, but it'll be building up that state of the program, and then we'll be returning stroke total. And we'd expect this, it's a floating point number, and Lua is formatting it in this very obnoxious way. But basically, this is just the number 2.
What do people use Lambda now for? Like, what type of business use case is there?
All sorts of things. It's kind of a hyper scalable way to handle user requests, because normally you have to provision a certain number of servers, and certainly the transition in like the early 2010s to the cloud, as they said, made it so that you could easily spin up more machines and also spin them down when you wanted to. But you had to like have long running machines, There's still this idea that like you're probably working on the order of hours. Lambda is interesting, and it has really sort of captured the most attention in things where you don't quite know how much computation you're going to need to do. You just need it to be able to spin up, do something very quick. You pay for it, and then it gets deleted, and you start again. And there might be bursts in the traffic, and you just don't want to have to deal with servers. It lets you just think at the level of like my program. People can have a lot of opinions about this, but that's probably the idea.
That makes a ton of sense. So instead of having to like have a long running server, you maybe have something that you're pretty sure traffic might spike at X date, and I don't want to have to go out and pay a ton of money for something that's going to be wasted time 90% of the time.
Exactly. Yes, precisely. And so here what we're doing is we're saying, well, okay, you could get that at a massively overpriced rate from Amazon, or you could go to any Hyperbeam node that will let you pay it, or if it's open, you could just use it. Like, at the moment, there's actually a bunch of open Hyperbeam nodes. But yeah, you could pay it, and you could prove the sort of security properties that you need about that machine, and then provision the service from it. Or if you didn't want to do that yourself, you can delegate to a router. So a router is essentially just another Hyperbeam node that knows about workers of a certain form. And we use this to say, okay, when you want to perform computation on a push node in the forward research Hyperbeam cluster, it'll point you to the right node behind that to execute your particular type of sort of shape of computation, you could say. But we also have what we call the green zone beta, which we've been running sort of on and off. It collapses sometimes. It's really is beta. But we've been running it for a while, and it is a TEE protected zone. So they all share the same key. In fact, actually, we could see this. This devcompute1, there's a devcompute2 that has the same identity. They can both sign with the same cryptographic key. And there's a router on top that you can go to that will point you to go speak to those nodes underneath it. And anyone that is running that same exact set of microcode, or as you saw when we booted up the Hyperbeam node, we can specify essentially the setups that we trust. Anyone that is running a trusted setup of the TEEs can join that router. So now if we think to our function as a service model, okay, well, you can just run a router and you could take a cut of the fee and route to only nodes that are running inside some kind of TEE or other trusted environment. Or potentially you could use that router to replicate the work. I mean, consider that the actual cost of buying bytes or at least the price to the Chia network, if you will, to buy bytes of storage over time is like almost 100th to sometimes even 200th of the price that Amazon is charging people. You could replicate this stuff a lot before and still be fantastically more efficient than Amazon.
I want to point out that we're casually pointing out how AO can basically with one blow annihilate entire categories of industry, right? Like we just casually said, oh yeah, Oracle is that multi-billion-dollar industry. AWS Lambda. This is even better. I don't think I've ever seen a demo quite so casually just laid to waste what are right now enormous, like entire industries.
Yeah, it's a completely new. We didn't intend to build AO Core. We intended to solve the problem of having AO LegacyNet, which itself was a hyperparallel computer, making it so that it was maximally flexible, so that the protocol didn't enforce rules that over time became a burden. We're really obsessed with this to make sure that, because the thing about a protocol is basically it's a point of coordination. We all agree that we're going to use the protocol, and then we never need to talk to each other again, and we can still interact. But if you want to come along later and change the protocol, well, now you need everyone to coordinate and agree and change the way that they're using it. So you must get the protocol right. And what we saw is, there's self-evidently demand for this type of hyperparallel computer. That's great, but we want to set ourselves up for success in not just today, but 20 years from now. And so the way to do that was to build a maximally flexible protocol. And I think by bashing our heads against this question over and over again, trying to work out, how to make it work in practice, we ended up with a design that just so happens to be so flexible that it really broke down what blockchains were trying to do and what Web3 in general has been trying to do into its primitive form, which is have a language to talk about verifiable computation, have a language to express the computation, have a language to talk about commitments on top of those and their verifiability. Then have a way to express not just one type of computation, right? You don't want to force everyone to be living in the EVM world or the SVM world or even WebAssembly, which is pretty good, but it makes trade-offs. it's not one size fits all.
Mm-hmm.
So made a meta virtual machine that allows you to express all of those different forms of state transformer. You put those things together, you get AO core. And I think we might have happened upon a really powerful primitive that just fundamentally changes the way the web works.
Okay. It's the coolest thing. It's the coolest thing. That's the only way. That's my layman's way of approaching it.
Okay, so let's. All right, we got it. We got to have function here. We can take this and go back to our Hyperbeam node, and we can say, oh, that's actually the wrong one. We want to be on our local, and we say, okay, take that and do add total. Yep, great, cool. But what we have here at this point is, so it's asking us to download it because it is it's a computation state. It's another message. And we can, instead, if we want to get it to format in the browser, so we can see what's going on under the hood. There's a shout out to Nick, who made a much, much, much nicer.
Go Eagles, Nick.
I don't know what that means. But yeah, he made a much nicer version of this as a graphical user interface. But we haven't merged it yet. I'm sorry, Nick. So today we're using this sort of slightly ugly formatter that we made. But principle is still the same. So you see here that we've got this message, right? And it's the output of this computation. And we can see also that it's showing us the linkage of like the, at least up here, the commitment for how it got to this state, the identifier of this. Yeah, if you just imagine all computations as basically positions in like this global, well, first you think of it as a tree structure, right? You've got like, you start with one state, you have this particular program, in this case, we add 2 to it, we're in a new state, and then we add another 5, which we'll do now. And then we're in the, state where total is 7. Great. We can also go backwards if we want to. We can go back to the state when it was just 2, and then we could fork on top of it. So we won't see this very easily in the browser, unfortunately. But under the hood, we didn't just go and re-execute the initial state plus 2.
Mm-hmm.
We used the pre-computed version. And then you realize that once you've got to the state, 5, you can actually, and this is something we're working on in the next release of Hyperbeam to make much more efficient, but basically unify that state with other states that also look like 5 when your next computation only depends on the key total equals 5. So then you deduplicate all of the computation in the world.
Let's talk about deduplication. So to me, that sounds like a massive efficiency gain, because you're basically saying, you don't have to go and run the same computation as Sam. I don't have to do it again over here. I can just almost like rewind time and get back to this original state.
Exactly. Yeah. So we can take our state here. We executed a couple of transformations upon it. We can go back to this one. We can say, okay, the ID is this. And we can take this ID, and now we can calculate the new ID. And this, when we go to it, is going to be 4, not 2, because we built on top of that state. So if we say total here, we have 4. Cool. But it's not like this version has gone away. We can actually go and execute on top of it further. We could say add 3 this time, say, and return the total. So now we've got 5. So that's kind of cool. We can reverse time, and we can pause time, if you will, and fork the state of the computation anywhere. So to go back to that function as a service example, imagine that you're actually like using someone else's function. And you think that the particular state at a point in time is useful for some reason. Say you're like, I know it's very crypto-y, but you're doing an airdrop.
Okay. Yep.
And you need I need to know what people's balances were at this point in time.
Mm-hmm.
Well, there's a reference for that. There's an address. There is always an address.
And you can't ask them, because they'll say, oh, it was actually XYZ.
Exactly. So instead, you've got this immutable reference to the position in the state space, the things we're at that point in time. And then you can do things like, map across all the addresses and send messages to each or transfer to each, how you want.
And then if someone else wants to do the exact same thing, they don't have to recreate the wheel.
Exactly. Yeah. And so if you look at it like that, you see that, well, it's laying out the whole global is not even the right word. It's kind of universal space of computable states of programs and making it into a tree where you can traverse. And each of the sort of branches of the tree, those like micro blockchains, if you will, because if you're on one branch, well, it has directly one ancestor each time, right? So it's kind of like a blockchain. Yeah, it looks like a tree. That's kind of cool. But it's actually deeper than that. It can deduplicate across, and this is something we're, improving in the next version. We're not sure whether we should call it like AO Core 1.5. I think it's the first major upgrade to AO Core.
Well, what about the milestones? So we did milestones 3.
Yeah.
We should just mix it up just to keep people on their toes. Milestone A now.
But milestone A. I mean, the big question is when we make Hyperbeam version 1.0, I think. Or whether this new version, the second. So what people probably, unless you're like following very, very closely, don't realize is that, last year, a year ago, almost, well, I guess it's going to be a few days in the past when you're watching.
Yeah, it's in the future for us, but by the time you're watching,
Exactly. A year ago, we launched the first version of AO Core, and it's basically remained unchanged since then. The core protocol is pretty rigid. We have this new version of it that's like an improvement in some of the semantics that we want to get in there before it's really, really widely used. But it has stayed essentially the same. So it's like, well, you want to say milestone 3 of like the transition of legacy net processes into this new machine. But AO Core has been like stable since the beginning. So I don't know.
People are going to love this.
Yeah.
So this is milestone 4 on AO Core 2. We should just go with names like Sequoia. Just like Apple does.
That's actually not a bad
You know that?
Yeah.
See, you're watching this in real time, people.
No, I think I can get on board with this. The naming is always, and people read them like fractions, right? So it's like,
yeah, no, I get why Apple goes with just like, Tahoe, it's just so easy. Yeah, it's so easy. One thing that turned on the light bulb for me is when you were kind of explaining the architecture of the internet, because a lot of what we're saying here sounds like super sci-fi. I know we're watching it right now, but it's just very advanced stuff. But then you're kind of just saying, Drew, like the majority of the internet is open source. It's just that the deep back infrastructure that the average person has no clue or cares about when they go and type in google.com or whatever. But that's all open source. That's all, and in many ways has this sort of the same principle that AO does. It's once we get to the last leg of the internet journey, which is the app layer, things have kind of veered far away from that. It's like a tale of two internets. And so a lot of ways, this is sort of like bringing the ethos of the underpinnings of the internet to something that everyone can experience on the consumer end.
Yeah, I mean, right. So we talked a little bit about the quantitative reason that anyone should care about this a while ago. But the qualitative reason, I think, is just as important, probably actually much more important, but it's qualitative. So, it depends on your opinions. But the way we see it is that essentially one of the core missions of the PermWeb is to make it such that there can be open source web applications. Like you can think of a Hyperbeam node as a piece of open, trustless internet infrastructure that anyone can use and everyone can pay the node operator for. We haven't talked about payments yet, but this is another part of the system. And when you have that means you can openly remix and reuse them for all sorts of different computations. One of the ways that you could use that is as the infrastructure that people run applications on. So as a PermWeb application developer, this has always been sort of partially the case. With PermWeb applications, you want to say like, hey, go and use, the GraphQL endpoint. And we'll get to that in a moment. And query it and find whatever data is on Arweave, use Arweave like your shared database, and return the results. And the idea has always been that you should be able to switch GraphQL provider. Problem has been that, well, because it's not trustless, we can't just have people, on their own hard drive at home or on hardware, run a copy of the indexer and serve useful data to end user results. So practically what this has meant, and unfortunately this is still true with the more recent changes in gateways, yeah, without Hyperbeam, like there just is no trustless way for us to offer the service to people, so we have to pay for it. And that's no good because we're like feeding the dragon to some extent. That money actually goes to AWS of all damn places. Yeah, precisely. So instead, what we can do with Hyperbeam is we can say, okay, we run one of those routers. We can farm out that computation to other TEE nodes that the community can then plug into. They can sell their service to the network, to other users. And from the developer's perspective, now there's gone from being like, 2 implementers or 2 or 3, depending on which way you look at it, of the GraphQL interface, to there being many, many, many people that will offer that service. And so then you should just be able to pull back that application like StarGrid, and it will run on whatever infrastructure the user wants it to run on. And this sounds like a subtle point at the beginning, but it's really not. The way that the internet works right now, if you build an app that other people like, you pay for it, not the people that like the app. And this is the seed that has caused all of the downstream effects where you basically turn every single service that we could want to use on the internet, every single service, into a company, where really it didn't need to be. It was just like someone threw it together in an afternoon. It was fun. If you have open infrastructure and permanent storage of the application itself, and by the way, from the developer's point of view, that costs like less than a cent most of the time to store. It's almost comically cheap. Any user can come along, they can recall it on any piece of infrastructure in the future and have it animated to come to life as an application they can interact with. And it costed you nothing as the developer. So now instead of it being like, okay, I built this fun thing on a Sunday afternoon, put it on Hacker News, and 100,000 people accessed it, I need to go and now start a company and go get venture backing and all the rest, and all the things that will eventually lead you down the line of. You could think of it like this, that the key factor that determines the future of a service on the internet is not the type of application itself. It's the type of organization that created it.
Mm-hmm, mm-hmm.
So in the desktop and the server world, and to some extent on phones as well, we have open source software. Right? Like people build the stuff largely for fun, and they ship it, and other people use it, and it costs the developer nothing when the user makes good use of it, and it improves their daily life in whatever way it happens to be. But on the web, because of the way the protocols are set up, we just can't do that. Instead, if the developer makes something fun and useful for other people, the developer pays for it. And that means that everything has to be a company, and just the nature of a company is that it will extract value. That is the point. To some extent, it's a mechanism design where we align people around the fact that these things should extract profit, and then we try and create markets so that they compete with one another to offer better services to people. But it is part of the model that they should be extractive of users.
I think that is low-key like the most, I wouldn't say the most critical point because there's a lot here, but it's the one that I personally find the most fascinating on an individual level, where you have entered this vicious cycle of it's expensive to start and difficult to start. You got to do it all on your own. So what do? You got to do? You got to go out. You got to hire people. You got to pay server costs. So if you're going to do that, well, you're not, unless you're already just born rich, you're not just going to do that for free. You're going to get your content. You're going to treat your users like customers. You're going to recruit that cost and along the way, probably and keep the profit for yourself. And then by doing that, you make future devs, their costs continue to rise because now you've created your own walled garden. If they want to access your services, they have to pay for it. So it's sort of like, it's breaking the wheel. It's breaking the wheel. I think that's really interesting. One thing I did find interesting in our discussion before taping was what happens for the few people who that's the dream, bro. Like I'm grinding away in Silicon Valley and I don't really have pure intentions. I'm picturing that sweet paycheck and I'm going to get my Lambo and my yacht. This would crush that type of person to some degree, would you say? Because if you have an open and remixable and easily accessible and low cost, no barriers to entry web, then their dev skills that they are hoping to create this walled garden are suddenly not that valuable.
Well, I think this is a wider question, but it's also sort of already true because of the it depends what type of development, right? Like Hyperbeam, we largely don't really use. I mean, we use like the sort of magic autocomplete version of AI, but not yet agents. It's just too in the weeds. For the context window, it seems is the big problem for agents to operate on usefully now. But if you're building web applications, like, man, that thing is so much better at JavaScript than I am. It's like not funny. So I think it does to some extent depend on. Look, I think things will just shift. It's like, what are the useful skills that people will want to procure? That is just now radically different than it was, say, like 2 years ago. And this, I think, provides, as we were talking about a little bit yesterday, a great framework for people to build applications extremely quickly on. It's like the walled garden around the application is just going to become less and less, would you say, viable as a strategy. And this will become more and more obvious over time, I think. I mean, it just makes no sense if you think about it. Okay, I'm going to vibe code an application for like 10 minutes. And then what? I'm going to go found a company?
Yeah.
To get, like this. No, it's going to take hundreds of times as long as building the actual application. What I want is a platform where there's already all the infrastructure and it can be offered trustlessly, so anyone can just pick up the infrastructure they want. It's really more like the relationship between a user and their ISP than the relationship between a user and Facebook and the Facebook servers. Yeah, with that framework and then an open library of content on top of it that you can just build your applications on top of, I think it's like almost an unbeatable combination. My hunch is that what will happen is that X, probably Alphabet, but definitely Meta, and maybe a couple of others, will attempt to build something that's largely what we're talking about, but the walled garden version. And then it's just going to be open versus closed.
Yeah.
It's really crazy. Like we're in sometimes things just work out.
Finally. I've been waiting for that.
We ended up in a very, very interesting spot. It's like what do you need in a world where applications can just be summoned in 10 minutes? Well, you obviously need a place that you can host them that doesn't take more than 10 minutes and really isn't the bother of the developer, you can say. Oh, yeah, we got that. Well, say you've got that then, great. But my content library is going to be empty, right? I start the application and there's just no content there. And what am I going to go do? Like make all the connections with creators? No. It just doesn't make any sense. What I want to do is I want to build on top of an open data lake.
You got that.
Yeah, funny.
Funny how things work.
Yeah, it is funny how things work. All right. Okay. So we upload our function here, or we could just upload a file like this. And, we got this demo.lua. It's going to give us back. Okay, cool. This version of the function we can go run. One thing that's worth noticing is that this Lua code that we've just executed, the internal state of that is now actually part of the external API. Like, as another user, I can go pull the state of our computation, not the parts that are like, let's say the developer spends time thinking about exposing, but all of the internal versions as well. And that, I think, is a pretty huge thing. You can also even, because of the way it works, it's just a giant pipeline. Here is a request that we can send that both uploads the function, and yes, that is a function in the URL bar, and goes and executes on top of it and gives us back the total. So you can Lua script in the URL bar if you were really so inclined. There's actually a ton of stuff about that. Maybe you probably don't want to put it in the URL bar. It's a little far. But about the embeddability of that's really interesting. So you could just have, for example, a HTTP or HTML form and have that post to an endpoint on a Hyperbeam node or on a router, or even just on Stroke, so that it goes to whatever server the user rendered the application on originally. So the user can basically bring their own infrastructure, and go have it process stuff just without any backend. No libraries, no backend. You just use the stuff.
It is unhelpfully novel. I'm like having a hard time picturing what. No backend.
No backend.
Yeah.
No. It's like in the same way that like a blockchain, where does the blockchain exist? one of the strangest things about building Arweave was like, I've never seen the thing. You know, you build something, you spend your
That is really funny.
years now. Yeah, I see sometimes pictures of people's minds, but there is no place in which the thing physically exists.
Yeah.
And this is the same. You summon the piece of computation when you need it from any one of many members of the network that will provide it to you. And then even weirder, the program states are all they all share that same property. Well, it's location independence, right? They're not tied to any physical place on Earth. Anyway, wow. All right. Okay. So yeah, the results, they can be encoded in whatever form we want. So say we've got this, that's kind of useful. We decide for whatever reason, well, what if I want it in JSON? I can just say, please serialize it for me to, oops, I've done that the wrong way around. Please use the serialize function of the JSON device. If I can type, there we go. Cool. And we get back the current state of the program. And so again, like there's a JSON device, so you can reuse the JSON device with any other random device you so desire. Okay, so let's try something more fun. All right.
Oh yeah, this is the one I'm excited for myself. This one is so cool, man.
Okay, well, no pressure then.
No pressure, no pressure.
All right, what we're going to do is we're going to ask for the committers on a message, and we're going to pick the first one, and we're going to return it to the browser. And then we just have this question mark bang, or exclamation mark, or yeah, all sorts of names for it, but we'll be saying bang in the demo. And what that's going to do on the Hyperbeam node is trigger it's a system that we mostly use for payments.
Mm-hmm.
Basically, a request comes in from the user, and you can configure a Hyperbeam node to do pre-processing on top of it. So there's an on-request hook that we can, actually, yeah, we can show this too. So if you want to know, so it's open public infrastructure, right? Well, one of the most important things to understand is how is it configured? As a potential customer of the system, I want to know like what it's doing. Mm-hmm. And so I can see here the node configuration. And there's an on request setup. And so we're using the auth hook device, the authentication hook, which has some sort of information metadata for the secret provider, which uses the HTTP auth device to basically do what we're about to show, which is make us a wallet.
Yes.
All right, so I'm going to log in with a username and password. And it, in the background, has just generated a wallet for me.
Mm-hmm.
And it's gated. Access is gated using, as we can see here from the configuration, by the HTTP auth device. Now, that could be cookies, or it could be OAuth. So you can make it so that someone logs in with Twitter or their Google handle or whatever you want it to be. It's openly composable. There's just a small interface that you need to implement, and then, yeah, anyone or any authentication system can have the same result, essentially. So it's generated a key for us. And if we're inside a TEE, we now know that that key is trust minimized. Like, it would take breaking the TEE or breaking Hyperbeam OS, which right now probably isn't that difficult, I would say. So, beta, don't trust it. But, we make it resilient over time. It's open source software. People can audit it for themselves. And then we end up in this position where, okay, yeah, the key is, I was going to say unencrypted somewhere. It's actually encrypted at rest on those machines. But it's not like self-sovereign in the same way that a key on your local machine is. But there is something pretty damn cool about it, which is that, you can access it just by going to any Hyperbeam node or any, they can actually sync these wallets between nodes depending on the access controls we set for them. But yes, you can go to any Hyperbeam path and it will sign it for you. And so here, if we look at, so we've looked at the committers to extract, that's the address that it has for us. And again, this is just like using the message device it's called. Committers is a function that it implements, and that results in a list. And so we're just going to the one key, which will return this first one. But we could also just as easily say HyperBuddy at 1.0 and format. When we do this, it's going to give us back the commitment that has been produced on our behalf. And here you can actually see the authentication. This is in dev mode, so this wouldn't normally show. Yeah, but you can see here, okay, we have this signature with the key. And this is really exciting because that means that we can interact with anything. So for example, we have another AO process that we set up earlier, and it's just a token, except it has this one sort of novel feature, which is just for the sake of testing, which is just anyone can mint. It's not a very good token. It's not very good value at all. But anyone can mint. And what we're going to do is go to that process ID, stroke push, and we have and bang again, and that's going to sign that sub request inside the pipeline. And we have action mint and the quantity 500. So we want 500 tokens. And now in the background, our node is going to be going and getting the schedule for that process, booting up this Genesis WASM is called, this like the legacy net evaluator. And then it's going to execute up to the present slot. And there we go. So it says warning, no target specified for the message. That's actually normal for a legacy net process because it's trying to send a message that we are not targeting to anyone. But then if we go and look at the balances, for that process now, we'll see that, I'm sorry, I needed to put, there we go. It's not a live demo until something goes wrong.
There you go.
Yeah, there we can see that somewhere in here will be our address. JE6, I believe is this one. Cool. Okay, I'll write it down here. We've got 500 tokens. And so now we have a wallet that is signing user requests for us inside a TE, or could be, here we're running it locally, but it could be inside a TE just as easily. Yeah, it's safe. We're accessing it through HTTP auth. So we just remember a username and password. And we can interact with all types of firmware applications. We can do essentially anything. In fact, we could send messages to Arweave if we want to. We can send base layer Arweave transactions. But let's say for now we just want to send, I don't know, some tokens to a friend. So what we'll do is, yeah, we just do essentially what we did when we were minting tokens. We transfer, and the recipient is the other address. We'll say Drew for lack of knowing your wallet address.
Yeah.
Although the barrier to entry to having wallet address now is pretty low.
I take free tokens. I'm not above free tokens.
He's not okay. Yeah, we can see Drew now has 150 tokens.
Yes, I've finally made it.
Yeah, that's
so what we're talking about a couple of things here, but we're talking, at least one part is sending tokens to people who asterisks don't have wallets. Now, I know that the wallet is being created within the T on behalf, and to access the wallet that was created for you, we can use almost anything like cookies, right? Or any other sort of authorization thing. So for example, if you guys are watching this and have ever participated in a marketing campaign where there's prizes, usually we have to collect your Arweave compatible address, send you the tokens to that wallet. I could just say, hey, I'm going to send it to your Twitter address. And if you log in from your Twitter address, correct me if I'm wrong here.
You would have to add OAuth to make that work. But because if we look in this configuration, like 95% of the stuff that's making this work, maybe more, would be shared between that OAuth version and the cookie version and the HTTP auth version. Sorry.
So no, that's the future. Everyone always says, like, what is the biggest hurdle to blockchain adoption is wallets, right? Like, my Nana's not going to sign up for a wallet, like
download a web extension. I can't remember the last time I downloaded a web extension, like voluntarily.
Yeah.
Outside of crypto, it's just not something people want to do.
Yes.
Yeah, like it shouldn't be necessary. You should just use all of the authentication systems that we currently have on the web, but just make those so that they can be trustlessly or at least trust minimizedly offered in a trust minimized way.
That is, to me, this is one of the things I think is most exciting to me. It's like this long sought after conundrum that, again, we just kind of solved in a blink of an eye.
Oh, it was a blink of an eye.
Well, I mean, me sitting here watching you felt very easy. I don't know how it was building it.
Yeah, I mean, well, I think we've definitely taken the approach starting about 18 months ago that now is just the time to go and solve the problems full stop. There's enough talk. Let's just do it.
Yeah.
And it's coming together. But it's a blink of an eye I hit.
Yeah. Yeah.
I'll call you next time we need help.
Yeah.
Your work on Drupal will...
Yeah, so it'll come in handy.
Yeah. So we can get the balance of the peer, or you in this case, for process state. But what if we want to make like a piece of remixable, usable infrastructure that is like, let's say, generally helpful? Well, how about this little Lua script? Here we got this function just called sum. And what this will do is it will add all of the values of keys that are integers in the message that we apply it to. So we submit this to the node. Now it knows what that is. We don't have to, upload it every time we want to call it, although we could if we really wanted to. Yeah, so we can now take this one, balances here, and we can say, okay, cool, that's great. I want to load up that process state. And now here is a key that's saying, hey, work out the current state for this hash path, which is essentially a process. A process is a immutable reference to a mutable hash path. Yeah, I mean, that's probably worth pointing out. Like if you're used to AO processes, you're used to the idea that you've got one ID that stays the same, but there's a schedule of inputs, right? Well, a hash path is essentially that schedule of inputs without the immutable reference. Or another way to say it is what we're layering on top of hash paths is an immutable reference. So some way of determining what is the current hash path for this ID. And that can, the current hash path can change over time, but that ID does not. Whereas hash paths, and really when we went like, you could say like, we started at the tip of the iceberg, then we worked out what the rest of the iceberg should look like. In that process of building AO core, it was really working out, what essentially now we can realize is, hash paths are just schedules. They're just not named.
They're just not named.
Correct.
Okay.
So when we looked at that example with the Lua script earlier, and we had the running total that we were adding to, that program didn't have universally shared state for different users, right? So in that example, we're thinking about a function as a service. It doesn't matter for any other user what's happening in the computation of another one.
Got that.
Well, essentially what processes are in smart contracts is really just saying, or blockchains even, I need an immutable reference, a way to get to some state that's going to change over time. And what that means under the hood is I need a protocol for resolving some immutable ID, some ID I can remember, like the name Arweave or Bitcoin, to some cryptographic data structure that's going to change. And in AO core, it turns out that just looks like, processes are really just immutable IDs that refer over time to a different hash path. We can remix and compose upon those process states just like they're any other computation state in the system. It's really just that a process is like one type of device that orchestrates a bunch of other devices to create the experience of something that looks like a smart contract. But you can take any part of that state and then, like we were doing there, going stroke balances. So evaluating the balance is key in that message. And we should say that like the messages are essentially just programs. In a sense, they're instances, at least, of a program of the type, in this form, message at 1.0, but it could also be Lua at 5.3a or whatever it happens to be. And so when you add we call them parts to the path, the HTTP path, you see this, stroke process ID, stroke now, stroke balances. Each of those keys is a different execution, like a call to the program that represents the state at that point in time.
Pods, right? Paths?
Parts. Path parts.
Gotcha.
Yes. So they're all just programs. You can chain them up, and there's no real difference between a process and anything else. So you can open the like smoothly go from something that's consensus based, something that's more like a smart contract, to something that's more like that function as a service world.
Mm-hmm.
And then even back, potentially, you can take the result of one of those, turn it into, if you so desire, another schedule, start scheduling on top of it, turn it into a process, do all sorts of weird things. It's like we simply cannot exhaustively enumerate all the different things you could do with it.
So remixing is on every level imaginable,
Yeah.
basically, from the most sort of minute atomic level up to whole chunks of programs, whatever suits your needs.
Yeah, precisely. In the same way that I think what we end up with at the end, I mean, it's a web of computation is something that hasn't ever existed before, as far as I'm aware. And if anyone in the audience knows that that's not true and they can point me to where, I would love to know, because I spent a long time trying to research. It's very, very uncommon that you come across an idea that is genuinely not, most ideas are, and well, even this is somewhat derivative in the sense of like about computation, but this is pretty far, at least as far as I can tell, from the rest of the the literature in this. I assumed when we first started working on it that like sometime in the 60s, someone had looked at, cryptographically linked distributed virtual machines. That's obviously a thing that people would build. But actually, no, the closest you get comes in the blockchain world. And they make this fundamental presupposition that you can intermingle the state outputs into the identifiers at each point in time. So they're like intermingling the output with the input, basically like a blockchain state. Arweave would be an example of this. Bitcoin, and all of them essentially. You have parts of the output entangled in the identifier. And that means that you can't say what you can with a hash path, which is go find me the result. Either work it out or find it pre-computed from someone else. I had this initial state, I had this program, and then I did this, this, and this on top of it. And you can pre-compute the address of that without actually doing any of the computation itself.
You're talking about like a very granular, almost native search functionality in a way.
It's the ability to talk about program states without executing programs. And that's what we need for things like verifiability. We want multiple nodes to attest to, hey, I computed this program state and you computed this program state, and we either matched and we can like combine the signatures on top of each other, or we can say there's a discrepancy. And then we can build systems for resolving those discrepancies. You get some other stuff like this operating system called Nix that in its package manager does something sort of close where you can say, hey, I had this initial like repository. They're not thinking about program states at all. They're thinking about packages of code, and then I added this thing on top of it and added this overlay, and then you get this sort of Merkleized log, if you will, which is similar to a hash path, but this is much, much, much more granular. Anyway.
This is such like a junior way of thinking about it, but it's like if this existed today. One thing that kills me about X/Twitter is instead of I love the Reddit up-down voting system, but I do like the Twitter format, and I really wish if I wanted to build basically Twitter, but instead of likes, retweets, whatever, you just have a nice little up-down. It would take me a bunch of time and effort I would have to redo everything from scratch. I'd have to guess how Twitter did it, and then I'd have to. With this, I can just kind of search for basically what I'm looking for and on AO processes, combine it together.
Not even AO processes, but that's actually a great prompt.
Okay, yes.
So excellent. So we've been talking about program states so far and their addressability. Like you have this reference that can point you to, hey, what are the things that I need to do to get to this state that we're talking about here, whether we're talking in the context of like giving a result to a user or making an attestation that some other node can then challenge, or combining attestations. All of these things, they all come down to this central idea of hash paths. But what if you want to like search from the other direction? What if you want to say, find me all of the known program states that have these keys and values inside them? Well, use GraphQL.
Okay.
Yeah. And so if you've been a developer on the PermawebOS for a while, you've probably used GraphQL as the mechanism for getting access to user content. It's like fundamental to the notion that we can have an open, composable data lake is that there's a shared index of all the data. If you don't have that, then it doesn't make any sense. And so this was one of the earliest sort of pieces of infrastructure that was built to support the PermaWeb on top of Arweave. Way back in, I think the first version was actually this thing called RQL, which my PhD professor had this really, I don't think, Simon, I'm sorry, but I don't think you'll mind. It's really very atrocious, I think is the right word. Simple language for this thing that we were teaching a course, and this was part of the homework, was building the simple evaluator of some language. And I stole a little bit of that code and built this terrible query language called RQL. Yeah. Which, if you were unfortunate enough to build a PermawebOS app, well, I mean, it was fun in a way. But back in 2019, when we were just getting started, it was very rudimentary, but that was the way to do it. We replaced it with GraphQL. I think it was 2019, early 2020. And that has been the shared language for how would we query across the data on Arweave. And, well, because we want to make a trustless, decentralized web, it's a necessary component. PermawebOS in a box has it. So let's take, for example, a query like this. So we have Apollo Studio here. This is just a simple way of showing like GraphQL queries and responses in like a nice UI where you can build them up. So we can see here we're extracting transactions. We're extracting the ID and the tags on them. Now, everything in Arweave land refers to tags. In AO, I think we broadened it to just be keys, because everything is really just a dictionary in this world, and it's easier to think about it that way. But we've added support for the old Arweave API. So if you're used to that, or you have tools that already use it, you don't need to change anything. You just run your queries and it just works. So here we're looking for messages that have type message as a tag and name target, a target key with this value. And this was the process that we were looking at earlier that has our sort of very non-value accruing token where you can mint any for free.
No, that token's going to the moon, I'm telling you.
Yeah, well, the supply is going to the moon. All right, as you can see here, it just ran on our local Hyperbeam node. So to make this work, we just conjured the query at 1.0 device and went to the GraphQL key, and we sent it this in the query parameters and the request parameters one way or another, and it has found everything in its local cache. Okay, that's kind of useful, but what if we want to return something that we might be able to use during composition? Well, we can just query it for any type of content that it has. It's not just processes that are stored on Arweave or their messages. So we have all of the messages here that this node knows about that were sent to the schedule of that process. But it's not just processes on AO that are obviously stored on Arweave. We could also, for example, change the filtration system here so that we can find all content that it knows about. That is, if we wanted to, it could be in videos, so we could find that short video we had earlier, but in this case, we might want to find all of the composable little bits of Lua code that has been uploaded to this node during our demos here. So it's currently executing that query, and it can find both of the IDs of the Lua programs that we use so far.
So if I have a idea for a video app, and I know, well, heck, there's a lot of video on Arweave, maybe there's some useful code as to how people, demonstrated those videos or shared those videos before. That way I can search, okay, I'm looking for videos, but I'm not just looking for the video itself. I'm looking for the program that delivered that video. Is that sort of...
Yeah, in the same range. We can find it's really just about locating content, right? Arweave is an open content lake. This is the language through which you can query it and see what's inside.
Gotcha.
Your local Hyperbeam node is always like you could say it's always a partial view of the global, universal computable program state space. And so what that means is that, well, if you want to, you can, so as we are now, run the copycat device, which has a GraphQL endpoint, just like we were using on the query device. But here we're saying, hey, go find from the other nodes that I already know about, go query them and look for pieces of data where the tag is content type and the value is application stroke Lua. And so now that's going to go out to the wider set of nodes that we know about and sync down that subset of the network. And then once we have it, so if we look at our node here, we can see it's doing a bunch of work in the background. Looking up different Lua scripts. And then if we run our query again, we'll find more scripts, the scripts that were stored on Arweave, not just submitted to our local node. There we go. And this can query across the whole of Arweave if you want it to, or any subset.
And this is trustless bundling that you were discussing in your prior video.
Not bundling. This is actually kind of unbundling.
Unbundling.
Right. I should say on top of this, we've sort of forgotten to mention, but yeah, this is trust minimized, if not trustless GraphQL, which again is a huge blocker, I would say, in making the decentralized web happen. Certainly in the Arweave ecosystem, and actually I don't know of any other community that has solved it either. We just didn't get to the point where you can trustlessly query across the data that's stored in the network. You always had to trust that the node that you were speaking to was giving you honest results. And you could do things like say, okay, you've given me this set of results, I can go download them. But the problem is, what if they exclude something? So the Graph protocol, for example, has a proof of inclusion in the results you get back. But that's not the hard part. The hard part is proof of exclusion. I want to know that node honestly gave me back all of the results that it knows about. It didn't censor them. There's someone on our team who made a salient point to me recently, which was that the way that most of the efforts to create decentralized or peer-to-peer web services have failed in the past is that the indexing layer is what's censored. And you see this today on Blue Sky, for example.
How so?
Well,
I'm very curious.
Because Blue Sky, they have one giant node, essentially indexer, which is the one that almost everyone uses. And it's a peer-to-peer network, so you can't, if people are censored from there, you can't censor them from the others. But practically speaking, that node is so important to the network, and it is trusted that you're more or less gone if you're not there. And so, with the system, and it's really TEEs. It's a mechanism of running arbitrary general purpose computation and getting back some kind of proof, or I wouldn't call it a proof, at least a commitment that it has been executed correctly that was missing previously. And then we added that to an operating system that you can boot in that TEE, which will then load a custom code, essentially, in this case, the indexes and the querying engine, and then attest to them.
When you say exclude and censor, why is that unintentional exclusion or intentional? Like, what are we talking, like free speech suppression, or what type of exclusion are we talking about here?
It could be anything.
Anything.
Yeah.
Anything under the sun. And so until we stamp out the ability for people to do that, then you can't have a truly sort of censorship-free environment.
Well, you need to have an environment where you can trust the machines you're speaking to are not being dishonest about the work that they've done.
So dishonest about what they've given you, and also dishonest about if they have not given you your full request.
That's exactly. Proof of inclusion is relatively easy. Like we could take any Arweave GraphQL server or gateway today and say, okay, take these results that it knows about and work out the Merkle path that gets you to them. And that would give us the inclusion proof. So we can know that it's a correct hit relatively easily. Although, that's still a huge distance from you can just point your browser at something and know that you can trust it, which is where we're going with TEEs, with HTTPS terminating inside the box. You can verify essentially by eye that the connection is secure without any tools, without that. That's pretty far down the track. But we could at least take external local tools on the client, and say, okay, here's an inclusion proof of this transaction under this query. That's possible. The hard thing is, okay, how do I know that you didn't skip something?
Mm-hmm.
And with the existing systems, without something like a TEE, actually, I think a TEE is more or less it's the only way I know that you can get this working today.
Mm-hmm.
Every other way is breakable. So it's a huge step forward.
Very interesting. I almost feel like we need, you know how we were talking about with the HTTPS, we got that little padlock icon? How can we get our own little icon?
Oh, we can use that. Well, it's funny, they removed the icon, right?
Did they? I haven't been paying attention. Is it gone now?
Boring thing now. They taught everyone for years and years, like, hey, you've got to look for the padlock. And
that's
now it's gone. It's under here. You can see it.
Oh, I see.
Because basically they swapped it. They said, like, if you go to an insecure website, they'll tell you.
Okay.
Yeah. Well, so where we're going, and like I said earlier, we haven't open PR for this, haven't merged it yet, but you should be able to. This, when we're done, we'll relate. I mean, not on this website, but on a Hyperbeam TEE node, this will relate to the key that is on the node.
So we'll see like a big chunk of stuff there for the TE, or
you'll see the public key in a form that you can verify by eye, looking on something like ViewBlock. So you can say, okay, I'm expecting to have a secure connection with this address.
Mm-hmm.
I can look up the address. I can see a transaction that is sent. I can see the public key in there.
Mm-hmm.
I know what I'm expecting to see in this box. And one problem here is actually that it's encoded in hex rather than base 64, which is really annoying. But we can make short, like simple tools to help people convert one or the other. But then you'll be able to verify by eye that you have a secure connection with the right node.
Very cool.
Yeah. No tools, just like the padlock. And then you know that every single result you get back. This is what we meant last year about expanding the edges of the network from like the blockchain is some separate universe.
Mm-hmm.
And then you use all these HTTP services that are completely trusted
mm-hmm.
and off-chain to access bits of its state. No, expanding it all the way to the edge. And even crazier, when the result gets back to the user's browser, this is what happens when we have any network request to a Hyperbeam node. It gives us back that blockchain, you could say like a stub, basically, this hash path that says, hey, here's the computation I did, and then that becomes mobile and challengeable. It's pretty cool. Okay, so we can see that the copycat device got 66 results from Arweave for us, and then we were able to query it, and great. Now we know all of the different results that at least our peers were aware of. And if this is running inside a TEE, we know we can trust that node has indexed them correctly.
Mm-hmm.
We still need to make it so that you can see a log of all of those indexing requests and how far they got. But that's say trivial relative to the size of the problem.
Mm-hmm.
And then you can say, okay, cool. So I know that this node has indexed this subset or has executed a full index of the whole network, and it's giving back these results so I can know that they're exhaustive or at least not censored. Cool. Okay. It's not just Arweave data that can now be accessed in the same form. It's actually all types of data. So for example, if we look at our computed state earlier, we can see Drew has 150 of these. Congratulations. 150 of these tokens or other address in XYZ, they got 150. So we could search for computed results. Now, we get back, here are all of the times that in our cache, in our Hyperbeam node's cache, not inputs, but outputs have been set to 150. Or one of these, rather, actually should be an input. This is probably, I guess that I imagine is when we are sending tokens from one node to the another. So that is an example of an output state. So if you're used to using Arweave GraphQL today,
mm-hmm.
you can now query not just compute inputs, but also compute outputs. Essentially, like everything in this sort of distributed graph of computation is now exposed via the same query API.
And you're doing that all through your own Hyperbeam node now in a trustless way.
Yeah. I mean, some interesting implication of all of this is if the data or if all of the inputs to a computation are stored on Arweave, then the output data is not stored on Arweave per se, but it is recomputable from permanent inputs.
Because if you know the input, you know the output.
Yeah, exactly. And how it's like a permanent implied or holographic or projected.
Is that what you mean by holographic?
Yeah.
So you don't have a written down record per se, but if you know the formula and you know the numbers in the formula, you can always recreate it. Yeah, you can project it.
It's projected by and so you can now query across and index those projected outputs as well as the inputs.
Cool.
Yeah, it is. Sorry, I've been waiting a long time for this, and now it actually works. So it's pretty cool. All right, what if we're back to kind of where we started. Finally, however many.
Back to Coinbase,
yeah, back to Coinbase. All right, like we want to go do something that is, I think it's fair to say, outside the design space of what we were thinking of when we built the relay device, or really any of these other devices that are used in this pipeline. But as a user, this is the classic way that all scripting works. It's like, you build the framework, you build the tools, you put them in a box, and then you let the user just like remix the stuff in a box in whatever form they want.
Mm-hmm.
And today we've decided that we want to know, what the price of Bitcoin and how much do you think it's declined by while we're...
Oh, man.
Well,
I don't even want to say. Maybe by the time people watch this video, have been going up for a while, Fingers crossed.
Maybe. Okay, so we can call the relay device with our parameter, but then we can chain up. This one interaction here has, let's see, there's 1, 2, 3, 4, 5 different devices used inside it in ways that the authors definitely didn't anticipate. But the result is that we get the price of Bitcoin at this point in time in USD. And so we can take the sort of input that we got, which came actually as a compressed message, like it's just raw bytes. But by using the different state transformers we have, we can turn that into something useful. And it's got a bunch of different elements that we can see here. And yeah, like, was it 600 different tokens? We don't want to submit all of those. So what we can do is we can upload a program, which we're going to call with. And what it's going to do is say, hey, give me the base message, but with only this certain set of keys.
Mm-hmm.
And so we can do that by, what do they say? In the UK, we have this like program called Blue Peter, where they have this catchphrase like, here's one I prepared earlier. I don't know if that's, no? Okay, not.
Is that like Ask Jeeves?
No. It's like, it's like they would always do these arts and crafts, and they would casually say like, and here's one I prepared earlier. It's like, there's no way you could possibly work out how they made this like perfect version of whatever crafty thing it was.
Sometimes the UK sounds like a foreign planet to me.
Yeah, it basically is. Okay. All right. So we make a program here, and what it's going to do is, and we upload it the same way that we were doing before. And basically, it's just that Lua function called with, where we just take the keys that are referenced in the request and put the ones that are referenced and not the ones that aren't into the result, and we return the result. It's just like a little bit of glue, I guess.
Mm-hmm.
So then we're back to our original path that started all of this hours ago, and we can execute it, and there we go. Now we have another Oracle result in the slots for that process. And what we did in order to make this work was take our previous pipeline and just add, it's so long it's hard to see. It's this component here. Yeah. So we set the module, and then we called with. That's our Lua program that we wrote. And then we said that the keys should just be USD and Euro. And then after that, we got the node to commit to the message. And then we even set the commitment device. And so everything's a device, everything's a message. Yeah, the different types of encoding can also be expressed as devices. So that means anyone can build an additional adapter, if you will, that can fit in with the rest of the system. And also the cryptography of the system. So you could plausibly bridge everything in IPFS, for example, into the system if you wanted to. Or really, yeah, that's why I was saying at the beginning, every computable state already has an address. Because you just need to work out some kind of basically mechanism of coercing the prior state and the request inputs and the output into a form, yeah, that basically is a message, but also has an ID. If you can do that, then everything combines together and everything already has an address.
Wow.
So here we're saying, hey, make sure the commitment device is ANS1 and 4 because we know that process we want to schedule on is only going to accept ANS1 and 4 data. Then we go to the scheduler device and we say, hey, method is post on the schedule. The target is this process that we made at the beginning. That's just a normal AOS process. And the subject, the thing that should be scheduled is the base, so the inbound from the rest of the pipeline, and then take that result and format it with Hyperbeam. And we can do it again, and now slot 12. And if we wanted to, we could just make this a cron path, it's called, and then it will execute every X period.
Automatically, cron jobs.
Yeah. Final thing to glue it all together, then you can add payments on top. So you can make it so that there's gating of the machine. At the moment, almost everything runs in free mode, but you can add, there's a bunch of different devices that let you do it. There's like this one called Simple Pay that just keeps a sort of local ledger, essentially off-chain ledger that you can, in the beginning, we were like topping it up with an off-chain like HTTP requesting component. It was a little bit complicated and weird. But you can make it so that anything that wants to can increase balances or control balances depending on some authorization schedule. Mm-hmm. So you might say, okay, someone has topped up on my website, for example, then they can use my Hyperbeam node. Would be one way to do that. Another mechanism we have looks much more like traditional token payments. The system called Hyper tokens, Hyperbeam tokens, and a P4.
Is Hyper tokens the same thing as LabNet?
No. Although the way that we intend to use them is kind of
together.
Yeah, exactly.
I see.
So in our green zone deployments, so everything's a device. There's about 60, is it approximately, devices.
Yeah.
Green zone. This is just like you want TEEs that do compute for people with Hyperbeam. To make that work, what we do is we have a router device on one machine that routes to other machines that have registered with the router, and when they do so, there's a authentication message. Essentially, you have to make return true. And that means we can program it with devices. And so that's where we use the snip device to say, hey, only allow people to register if they're running this piece of firmware, this operating system, and these node settings. Okay, inside each of those nodes, we then make it so that you can, each has what we call a node process. That's another device. Kind of getting there. There's devices all the way down.
There's 60 plus. I'm beginning to memorize them.
Yeah, but each is composable. So we built them because we needed to solve like one particular problem. But they're massively reusable, just like we found with this one here, where none of this was what we intended it for.
So I could like merge devices or take apart a device, same thing.
Yeah, and create devices on devices. Right, like
where one device is really just too synchronized.
Yeah. There's one called apply that lets you like make things that act like devices, but using these sort of scripts.
It's a device that makes more devices.
Yeah, it's a device that outputs
okay.
devices. Anyway, okay, there we go. I mean, this is what we've been building. We're pretty excited about it.
Dude, I cannot imagine what it's like to have been grinding on this so long and finally have an opportunity to really show in detail and a live working demonstration what it's like. So it's It is fundamentally rethinking how we view the single most important invention of our lifetimes, which is arguably the internet. So, Sam,
Thanks.
can't wait to see what we got next.
Well, let's make it stable, fast, and widely deployed. That's the mission. Like everything is now basically there in beta form, like for the whole PermWeb stack. But like, it actually worked pretty well today.
It worked well.
Yeah, there was like one moment we had to do a little bit of magic behind the scenes, but
No, we didn't. We didn't edit anything
we
out.
did. I mean, we just reset a local node. But there's a ton of stuff to do. But it is a moonshot, and this is why we're obsessed with it. We think this is a big deal if we get it right.
You heard the man. Thank you all.
Thanks, everyone.